So welcome everyone to another iteration of our user group. Today we will be talking about RavenDB and what it is will his creator tell us in a bit. So thanks to all our sponsors and they're especially our Go sponsors that help us to run this user group and cover its costs. Who are we? Jose is our founder. He started this user group years ago, and we are all helping him. So there's Pavel, there's me, Nigel, Laurent, Fabian, and Mark. What are we doing? We organize events. We try to connect developers with developers, organize beer and pizza with our user groups. We used to at the last user group event in Zurich, which was a couple of weeks ago. We did it again for the first time since 2019. We hope that we can do more of these. So if you want to host the user group in an in-person event in Zurich, just reach out to us and we can see that we organize that. What can you do? So follow us on Twitter to further our reach and be connected with us. Join our meetups and help us get more people to .NET. So if you have colleagues or in your company, just tell your colleagues about it and get more people to us. What we also always need are new speakers and new content. So if you want to get started with speaking, do it with us. We can guide you along and you will have a kind audience to try your first talks out even. There's an event here in Zurich that is a partner event, the .NET Days. So if you live in Zurich, you can get tickets and go on the 30th of August to the .NET Days. It's a conference all about .NET and it's a quite good conference. Today, our speaker is Oren Eini, and he is the CEO and founder of RavenDB. So he wrote it, and he's also a fellow MVP colleague. And with that, I hand over to Oren.
Thank you very much. Hi, everyone. Give me a second to just do the setup. Can you see my screen?
Yes.
Okay. So I'm going to talk to you today about RavenDB or about databasing in general, because I speak about RavenDB all day. And I think it's more interesting to have a bigger view of things. So the first talk that I'm going to do is about how do you model data in a non-relational database? And that tends to be quite a surprisingly hard thing for people to do. The next thing that I'm going to talk about is going very deep into how exactly databases are built and all of the experience that we had in building RavenDB. Throughout all of this, if you have any question whatsoever, ask me right now. I would very much like this to be a debate and hear from you about anything that you want to clarify or want to go over or anything like that. And with that, let's talk about modeling. Why do we need to discuss modeling? I mean, the business comes and says, I want a login page. I want to be able to order chicken or eggs or milk or whatever. And I just do that and move on. What is there to think about? And it turns out that you don't really need to think about modeling if you have a very small application. Because whatever the user sees, this is what happens in the backend, and that now you're done. But as the complexity of the application grows, and this happens on day 3 of any application I've ever seen, then the amount of work that you have to do in order to actually do whatever the business wants increases. And I will give you what is probably the most simple example that I can think of. Let's say that they have some noise in the background. Let's say that they have an online order system, and I want to buy this pen, this marker. So what data do I need to keep? I need to record that I sold the marker for how much. That's what it is, right? Except that I also have to do taxes. I have to deal with inventory. I have to deal with projections on when I need to renew my inventory. I have to consider loyalty program, payments. Maybe I'm paying using multiple credit cards. Maybe I'm paying some in cash and some gift card, and a bunch of other stuff like that. And suddenly, what used to be something very simple become incredibly complicated. And this is, we're just talking conceptually. And the more data you have, the more work you have to do, there is a huge problem. How do you store and create that information? And the most common way of doing that is to use a relational database, where you have tables, rows, and columns. And you're familiar with the terminal forms, and you have a fixed schema, and everything is great. Because this is how we were taught in university, this is how it should be. But we have a problem. And the problem is that as the level of complexity grows, this becomes almost untenable, both in terms of the complexity of reading and writing the data from disk and from the database. Reading from disk is for the other lecture. And from the perspective of how much work the database needs to do in order to get the data that I want to show. So one of the interesting things is that you have a fixed schema, and every value, you just have a single value for every column. Now you can throw a JSON string into a column, and that sort of works. But you lose a lot of the capabilities of the database, such as being able to query that, indexing that, aggregate. Some databases like Postgres has some capabilities of that, but the performance and overhead is still quite significant. So they would rather use normal tables versus just use JSON values. When I read this book, the refactoring database book, it was, I think, close to 15, 20 years ago. And it's a really interesting book because it tells you how you can modify data. But this is a 400 plus pages book. And it tells you in excruciating detail what is the process that you have to do when you move from first and last name to just name, or the other way around. And that's a pretty big picture. Now, the moment that you start working with more complex things, I have an order may have many different items. So typically I have the order lines, and then I have the products. If I want to render the order, well, I have to do queries well. If I'm working in an environment where my data isn't fixed ahead of time, if it's user-generated data, if it's coming from multiple sources, stuff like that, it's becoming quite hard to do. And another really big problem with relational modeling is when you do that and what do you normally do. Consider, you start a new project. What do you do? Well, the first thing to do is to define the schema, right? Because that's what you do. And how much do you know about the project on the very first day? By definition, almost, the least amount of information, but you're already pouring concrete into your design. Because you find the schema, changing the schema is hard and or awkward at least. And once you put the data in, now you have to do data migration, you have to verify data working. It's not unknown to spend several weeks building and debugging scripts to do schema integration that only run once, but they have to run properly. So there is a lot of complexity around working with relational databases. And one of the reasons that I built RavenDB was to address that. So let's see how we can do it. So we talked about the schema at the start and the modification, but another issue that we have to do with is the complexity of actually managing this. And if I have never seen a DBA who didn't have a story about, look, I went into the database and there was this huge dog query and I fixed that by creating an index, which is, let me translate that from DBA speak. They use a linear scan on the data instead of doing a hash table lookup. That's pretty much what they're saying. Or worse, ON squared versus O1 operation. And it turns out that for the most part, you have quite a lot of work ahead of you if you want to maintain good database hygiene. Now, here's an interesting question. What does a non-relational database look like? I want to show you this. This is, I'm going to put the URL in the chat. This is a public instance. Any of you can go and look into that. And I have some databases here. This is some sample data. And now you can see here is a document. And ignore for a second the details about the UI. This is the data. So this is just JSON. And in this day and age, if you're in this meeting, you know what JSON is. So what's the point? Well, this is a discussion about modeling. So let's talk about this. How do I model complex data? And I really love this example because I have here somewhat complex data. I have an order, it has multiple order lines, and shape to something like that. If I would try to put that inside a relational database, I would need 3 or 4 tables just to render a single order. But look what I have here. All of the information is in one location, right in front of me. And it turns out that this maps very, very closely to how my system actually operates. Because I'm literally just taking the objects that are running in memory and shoving them as JSON into the database. And now it's the responsibility of the database to make sense of that, to give me features such as transactions, to give me features such as queries, all of that. Not on top of some mythical schema that I created at the beginning of my project, but on something that I'm working on right now. And that leads us to something that is called the impedance mismatch. Because when a user looks at my system, they don't know how the data is stored in the backend. They don't care. So what they're actually looking at right now is the user interface. And they believe that there is almost certainly is a one-to-one match between what you see on the screen and what they have in the head. But in the backend, and going back to this thing, this may result in multiple tables. So the idea here is that we're going to skip the idea of impedance mismatch and just do one-to-one mapping. It does lead to an interesting conundrum. Let's consider this scenario. I have an order that have lines, that have products, have a name. What's the problem here? The problem is that up until this point, I was great. But here I'm traversing from the orders document to another entity. Now I can do that. I can serialize that just like that. But what would happen? At this point, I would have something like this. bunch of other stuff like that. So if I try to do that in a naive manner, every time that I want to serialize an object, everything that it touches would be serialized with it. And if I have a highly connected graph, well, what would happen? Every document would effectively be the entire system. But one second, I have an order, and the order says that I bought, I don't know, this pen. And this is a green pen. But apparently, this is now no longer green. This is azure, whatever. So I need to update that. But where do I update that? Do I go and search through all of the orders in the system to update the relevant product? This seems like it would be quite costly. And it calls back to the notion of third normal form. So the issue that we have to face is that, yeah, it's easy to say, oh, just store the data as JSON, but we still have to deal with how are we actually going to model the data, because there is absolutely still modeling work that we have to do. So before I start talking about this, I would really like to have your opinion. How would you approach modeling something in a non-relational environment, where the unit, the basic unit that you have is a JSON document? So think about this for a second. And I want to call you to something. This is a great book, The Domain-Driven Design by Eric Evans. It's, dear God, it's been more than 20 years since it was published. Almost 20 years. I think it came out in 2002, 2003. But it's a really influential book about how you should build your software. Interestingly enough, it does not talk about persistence at all. So it doesn't care how you store the data, just how you model that inside your application. And that leads to an interesting issue. What am I actually going to do? I have order. What is it? How do I refer to that? It's easy to say, oh, this is I use that to refer to order. But in domain-driven design, Eric called that an aggregate. An aggregate contains line items, payments, anything else that directly relates to the order. It also has references, other aggregates. And what other aggregates may I have in this sort of system? I would have the product, because the product has its own independent existence from the order. And the basic rules goes like this. An aggregate encompasses everything directly related to this. I can speak about my finger, but it is always my finger. So I can speak about line item 3 of order 16. But the name of this line item is always bound to an order. Therefore, it's wholly owned by this. Now, why does it matter? It matters because it gives you some really interesting opportunities to design your system. Let's talk about this. An aggregate is the unit of change. It's the unit of business consistency. It is perfectly fine, for example, that I may have something like this. Business rule is that closed order, zero balance. Okay, what does it mean that the closed order has zero balance? It means that the amount that I have here, the payments and the discounts and the actual cost of the items should end up with zero. So no, this is no longer an order that still needs processing, charging, something like that. Now, why does it matter? Because everything goes through the order, through this aggregate, then this is now a very easy rule for me to apply. But if I have the notion of line, which is an independent existence from the order, it's very easy to get into a point where I added the line and didn't check that the order was closed. Or worse, I have to deal with concurrency situation between them. So the whole idea is that I can treat the order as a single unit, and that's the level of consistency that I have. Every change to the order, or every change to the order, adding a payment and a discount, is a change to the order as a whole. Conversely, references to other aggregates are not bound to the same level, to any sort of consistency. What do you mean by that? If I have two independent orders, there is nothing that I have to do to serialize or to synchronize between those two orders. If I have an order in product, well, they're completely independent of one another. I can go and add an item to the order at the same time that I'm modifying the product description, something like that. It turns out that this concept of domain-driven design makes a lot of sense when you try to model non-trivial business scenarios. It also ends up being an interesting dilemma. Why is that? Think about it. When we work in business, when we talk to the business, they don't think in terms of data. They think in terms of paperwork. Did you fill form 103? Subsection C in form 18 hasn't been properly filled, therefore we cannot release your cargo to whatever, stuff like that. Well, paperwork is just another way of saying documents. So now we have a far closer mental model to what the users actually see. And now all of this cost of translation, both from the mental model that the developer has to what the business is, to how we persist and operate, are almost completely gone. We still have to talk about this. Because when I'm referencing another entity, another aggregate in my system, it is important to know there is another rule. And this rule is that you may not refer to anything except another aggregate. What do you mean by that? Let's say that this thing has ink in it, and this ink may need some permit to import something. So I have a permit for pen, and this is a particular pen in the particular order. This is not valid to do so. From a modeling perspective, why is it invalid that I'm referring directly to a line in an aggregate? Can you think of a reason why this is invalid? The reason is actually quite simple. This is the level of consistency. If you refer to something inside this, nothing guarantees that it will still be consistent. So you're not here. This is if you have a permit or a permit process, whatever, you always refer to the order, because the order is the unit of consistency that you have. That's the aggregate that you have. Now, I want to give some concrete examples about how you model things in non-relational format. Before we do that, I want to give you some ideas about the capabilities of RavenDB, because that's the example that I'm going. So right now, we have a document, just some JSON data. We can see that we enabled the revision for this sort of documents, and that actually gives me diffs of what changes happen in the document over time, which can be quite interesting to work with. I can also work with the data in this form. I have a document may have attachments, just like an email may have. And here you have, this is the Laura, and this is the employee field. We can be a little more creepy and monitor the heart rate over time. So this is a Fitbit style that for some reason we keep about our employees. Actually just to demonstrate the time series feature. So the idea here is that you're not bound to just storing the data as simple JSON. You can also have dedicated support for doing all sorts of interesting things, such as time series, binary data, and things like that. Now, I want to show you something interesting. I want to show you how I actually query this. City, nothing. But notice that this took 337 milliseconds. In order to have to London, and this took a lot less time. So first of all, a couple of things to note. I'm writing queries in freeform, and I'm getting the results. There is no mental hurdle to jump through. This is there is a reason I use the term non-relational versus the term NoSQL. RavenDB is a non-relational database, but as you can see, it has quite a lot of SQL-like syntax. Another thing to note is look at this index. This guy was created when I issued a query. You can see this is by city and on orders. Now I'm going to go here and ask it would help if I actually do this country. And now you can see here is the ship to city and count, ship to city and country. And now this is gone, and in a few seconds, this is going to go away. So what ended up actually happening here is that I'm running my queries as one does against the database. But what actually happens behind the scenes? When I'm running a query, it goes to a query optimizer. And we have to figure out what is the best way to run it. What if I don't have an index? Well, you know what's going to happen then? The database has to scan through all of the data in the system. This is where we play the set-top box, because it works great if you have minuscule amount of data. But the moment that we have something even slightly more serious than that, then it goes away. And let me show you what I mean by that. This is another RavenDB instance that I'm running. It is currently being loaded with some data because I want to run a performance test. I want you to take a look at this number. This is 203 million. 203 million items. And we are pushing data at the rate of 50,000 per second. Why? Because they actually need to run some performance tests on queries, and it needs to be big enough to matter. So the whole idea here is that, now try to imagine, this is currently taking 125.6 gigabytes of disk space. What will be the cost of querying something like that? It's going to take a while. It's kind of sucks. So RavenDB says, no, we're not going to do that. Instead, we are going to go ahead and use an index. In this case, I'm using an index already made. And you can see that I joined this team. I joined Reddit in 2009. This is actually, I have 69 million something users. And let's search for John Doe. Now, apparently quite a lot. And do we have Jack? So I want you to pay attention to something like this. What's this number? This is how long it took me to do a query on this collection. So close to 70 million documents. And the idea here is that I can use an index to do that. And we actually talk about this in the second lecture. But the more that you query, the more information RavenDB has about what you're doing. And then it can generate the optimal set of indexes for your needs. There are other things that are really interesting. One of them is that a document is composed of several things. You have the ID, you have the data, and you have the metadata. You have the ability to control all of them. I also want to show you how this looks like when you're actually working from C#, for example. And we have a great example here. So I have some POCO classes, plain C# classes, nothing behind my stable, something like that. I open a session, I store some of them, and I call save changes. It's important to understand this is actually going to create a transaction. So all three of these documents are going to be modified in an atomic operation. This is how a query thinks. So I'm using a link. But I want you to pay attention to this item because this is really important. What am I doing here? I'm saying, give me all of the orders where shifted is not null. So let's look at that. Here's my query. That's great. Now, what I actually want to do, I want to count this item. I want to update this value. Well, what do I have to do now? For each one of those, I have to go and load this document, right? And then I have to go and update it. I have 809 items resulting in these queries, in this query. How many times do I have to go to the database? Let's look at this one. Just for this guy, I have to go to the database 7 times. And that's absolutely insane if you think about it. Now, how do you handle something like that if you're running using SQL? You can do a join, you can try doing prefetching of the data, something like that, but it's really complex. With Raven, what I'm saying is this. And this is what this time will generate. So here's the data. Same thing as before. What happened? Nothing changed. Notice that I have 2 tabs here. What's the idea? The idea here is that I'm going to the database once, but I'm telling RavenDB, hey, I'm also going to want to load this related document. So in one round trip to the server, I'm getting all of that. In terms of the code, all of that is loaded. Here, I'm only getting orders. But all of those items are cached in the session. This line does not generate a query to the database. It can be served directly from the session. And it turns out that this has impact on the way that you design your system. So now let's look at some scenarios and see how it works. First example that I have is a hotel reservation system. And I have rooms. Rooms have many features. And I have to do something with availability. By the way, I hate those sort of systems because it turns out that what you actually need to do, you need to query for the absence of a value. I have a room, the room have reservations. Give me rooms that are available in particular places. Find me the absence of a value, which is really unknown. Now, I want you to just look at the amount of details that I have for a room. And this is truly a simple thing. I have all of the features in the room. So bed is a double or a king or whatever. I have a poolside view. Maybe it's wheelchair accessible, smoking, non-smoking, a whole bunch of other stuff like that. Now I want to be able to run searches on that. I want to have a wheelchair accessible room with double bed and a poolside view and whatever. The minibar is whatever the minibar, maybe I have a minibar menu for a vegetarian or there's another more vegan. There's the vegetarian, the vegan, or things like that. Now, I have the availability, all of the invoices, everything now become quite complex. When you start thinking, okay, how do I store all of those sort of things? So let's look at it. So the first thing that I want to do, I want to actually model them as simple documents. So I have this thing, Sheraton, blah, 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 blah. And now I'm going to say, hey, I'm going to, in terms of modeling. This is my room. By the way, it's very obvious this is room 821, so I know which floor it is, everything else. Now I'm going to do, this is one document. This is another document. Why do I separate them? Conceptually, I'm going to say something like, hey, what are the pieces of data about the room that belong together? So all of the amenities, all of the features of the room are in here. The availability of the room is actually a separate concept. But I still like it to be right near one another conceptual. So I create this logical separation between the pieces of the data. By the way, this is actually really cool because I can just write, now I can query on what is in there. So I would have something like this. Form, to, etc. Very similar to how you would keep it in pen and paper. And it's actually really surprising how often that mental model, how do I keep it in pen and paper? How did you used to do that before you had computers? Is such an important simplification to the overall model. Now, I can run on the availabilities, and I can do something like this. Now, I want you to look at this guy, because this is really interesting. What do we have here? I'm indexing the availabilities. I'm indexing this document. But I also need to do a search by this document. Let's see how that works in a live system. Here you can see I have Steve. Steve reports to this guy, Andrew. Now, what happens if I wanted to do a query? Give me all of the employees that report to Andrew. Well, it's very easy to do that, right? From employees. Okay, so this is the guy, employee number 2. Here, everyone that reports to Andrew. But I had to do 2 separate queries in order to do that. I can do it differently. And now, what I'm saying, by the way, notice that what I'm actually doing here, what I'm actually doing here is writing link query. Now I'm going to query by. Now, this is actually quite interesting because what happens if I go here and I'm going to say that, hey, Andrew, you no longer Andrew, now you're Mr. Funny Name. So this is quite interesting because what does it actually mean? I have the ability to do searches, not just across a single document, but across document references. That means that I have far better system to model the complexity. Think about how I would express something like that in SQL, where I have to do many joins. It's become really complicated to do that in an efficient and optimized manner. So this is an important note. The data is residing in documents. This is the business scope. This is the level of consistency that we have. It's very easy to load with working with related data. We saw the references between documents, we can include, we saw the load document, so we can index related documents and keep it up to date. And move to there is no need to deal with a treasure product. There is no need to worry about, oh, I have to do complicated nested things. Complicated nested things generally don't happen because you already have a good structure, because you can put complex objects or object model into a single document. Let's look at something else. Product catalog is a nightmare to deal with. Every single item is different. Except for maybe color, there is no shared property between shoes and TVs. And even so, TVs are not just black. So I think we can skip the color description. So now we need to do a whole bunch of interesting details. First of all, we have to support dynamic data. And it turns out that this is actually quite easy to do, because I can go here and say, something like that. Now, how do I search for something like this? Well, you just do. That's interesting. Oh, because it's, sorry, different. What it So here's the search that I run. It matters about the complexity in which you're working. But there is another issue. Here is a scenario that is really quite annoying. I want to be, you're familiar with those sort of things where I have to slice and dice data? Let's look at our orders. So yeah, the orders, I can say were total greater than 500, and it sliced the data. Now, I want to not look at, 600 items. I want to be able to narrow things down for myself. So I can do it like this. So I'm running this, and look what I'm getting. It sliced and diced the data for me, and now going from here to here is trivial. I can actually do this in a more interesting fashion because I can also do this. Now I have two of them. Now how many orders I have for each company? And again, the whole idea is that we want to make those sort of things easy. And it's crazy how complex that can be, just doing this. And now I can start filtering this out and all of the relevant things. Now, let's talk about something like this, import-export. I mentioned pen earlier, but apparently there's so many rules for getting things in or out of the country. For example, if you're talking about food, then every single type of food apparently has a totally different set of regulation. If you're importing alcohol or milk, crazy levels. If you're operating toys, then what regulation does this subscribe to? Apparently, if you have a rocker for a baby in Israel, I don't know how to say it, like a baby seat that you rock the baby to sleep or something like that. And it's not meant to be, it's not a safety seat, it's just something that sits in the house and they sit on. Apparently, the regulation said that you have to put a 70-kilo bag of cement on the item and leave it for 24 hours, and it has to hold 70 kilos. I don't know what kids they have that require that, but that's absolutely insane. So each one of them have very different processes and regulations. So how do we manage it? And we come back to, oh, I want to be able to be as dynamic as possible. I want the database engine to allow me to be dynamic, but at the same time, it's trivial to just store opaque data. Here's a string. Everything can fit in a string. I used to work for a client where they had strict rules and regulations about how you were expected to modify the database schema. You had to submit a paperwork, and it had to be by Thursday, and then it would be brought up for consideration at the DB meetings on Friday, next Friday, by the way, not the same Friday, because all labels always look 1 week back. And then they would approve or deny it. If they would approve it, they would schedule it to be deployed in 2 weeks, which meant that best case scenario from wanting to modify a field to actually doing that was 4 weeks. Practically speaking, here is what developers did. You see this guy? This is actually int32. Age is this range. And that's what they do. And I see people are laughing here, but I will say something nasty. May you debug such code. And yeah, much help is going on. So the whole idea is that we want to, as much as possible, to match the business. So there is a lot of flexibility from the business itself. And it needs to also be reflected in bucket. And a bucket needs to allow you not to, oh, I can shove another 3 bytes in there because it's free. It allows you to do the query, to do the operation, something like that. And in many cases, the idea here is that you sit with the domain experts, the people who actually care about, because I'm assuming that as a developer, you're not up to code on all of the dairy regulation rules for import into the EU from another non-EU country versus EU to EU or any of those sort of things. And in many cases, if we can break it to a one-to-one mapping between what the user is thinking about and what we actually work with, it makes things a lot easier. We're almost to the end of this part. If you have questions, I remind you, feel free to ask them whenever you see them. Rental management. This is another case where you have a whole bunch of data and details. But you know what is shared across all of them? The physical representation of documents that you're signing on, the list, the number of guests that you allow, stuff like that, one-to-one to how we want it to be in the database. There is no thinking involved. This is the UI, throw it to the database, pull it out, query, operate, and move on. And then you have things like that, payment tracking. Apparently, it seems, it looks like it would be a very simple thing to do. How much, you know how much the list is, so you know how much you're supposed to pay. But there are utilities, there are taxes, there are amenities that you might have used, maybe it's room service, something like that. And apparently there is this whole body of law that is related to how you're actually accepting money from a tenant. For example, in Colorado, in the USA, let's say that you have the following status. Payments is lease of $500, utilities, gas, let's say, $50, something like that. And I paid you $420 for whatever reason. How do you decide what to do? Did I actually pay the gas or not, or did not pay the gas? Apparently, there is a whole body of flow around exactly how to do this computation. But The whole idea is that now, how would you model something like that? Well, department charges. Now you have everything in here. This, the gas, electric. Now you have the actual payments, and you're tracking that. And now it is trivially easy from a modeling perspective to see how the payment is 420, but how much of that went to each one of those items. Instead of trying to do this in some amorphic fashion. This actually matters because then you have to actually pay the gas company. That is it. Okay. So that's now is the time for questions. Feel free to just ask them live or throw them into the chat. We're very happy to answer any more questions that you have. In the meantime, I'm going to take a breather.
Yeah, we can do, I think, a 5-minute break. Everybody can do a bio pause, get new drinks. You can also bring beer. And then we start in 5 minutes. Was really interesting so far.
Thank you. I'm very happy to hear.
Keen on the next.
Yeah. So just to give you a warning, this one was 14 slides. This one is 58.
Yeah, give us all the knowledge.
I'm going to get me another cup of coffee. Yeah,
Okay, there's a 5-minute break. We will be back at, let's say, 5 past, 6 past, around that. Okay. So we will be back in 2 to 3 minutes. And if anybody has questions, please shoot. It's always nice for the speaker to have a bit of engagement and if people have questions.
Hi.
Yeah, hi, Adam.
Hi, how you doing? Feeling good? It's a little noisy where I am at. That's why I'm typing in the chat.
No worries, no worries. I think Oren is anyway taking his bio break, but that's a good question. I mean, we use personally Mongo.
Sure.
So Oren, there is a question, and so that we have a question, and that is, I mean, the same is for us. So you probably get it often. So how would RavenDB compare to Mongo, for instance? Because they are like really similar, or are there differences?
RavenDB and Mongo are similar in the same way that a cart and a trainer in many respects. And I will explain why that matters. Consider try to do that in a proper way. So I will show you. This is RavenDB, okay? If you want to use Mongo, this is what you can. Now, this is not a fair comparison. There are GUI utils for the GUI utils for Mongo, obviously. But I think that this is a really good example of what matters. So here, so it matters when we put a focus. For example, RavenDB has been transactional from day one. In Mongo, even today, you have transactions, but they have far greater performance costs than non-transactional events. If you had the need to administer a MongoDB instance, a MongoDB cluster, then it's quite complex to do so. If you look at the API that we provide on pretty much any feature that you want, it matters quite a lot that you have strongly type, you're working with objects, you have a unit of work, density map, all of the things that you're used to in terms of the benefits. We have, and I'm trying to summarize a quite complex topic, but to give you some simple examples, if you want to deploy a cluster of RavenDB nodes, I actually have a video. I'm doing that in 10 minutes while I'm speaking. If you want to deploy a cluster of MongoDB nodes, then you have the MongoD, MongoS, there's a bunch of separate services that you have and demos that you have to run and configure separately. I will give you a small detail. There used to be worms that would go around and attack vulnerable MongoDB instances. And they would do that because people would push production systems to the public internet with no security. And our reaction for that was, hey, if you want to publish something with no security, we will physically stop you. If you try to push a public RavenDB server on the internet, then you didn't set up security, then the server will refuse to run. It will actually run and tell you, sorry, we're not doing that. and give you the instruction on how to fix it. And that's an important mindset. Some of the features that I've shown, they include the facets, the ability to, I haven't actually shown that, but I can do something like that.
What I personally always liked, I mean, I haven't used RavenDB, but I looked into the documentation a bit. And what I really like is the way you interact from a .NET developer's perspective. The API is very pleasing, and looks very nice.
Mm-hmm. To show you here, you can see I'm doing a full text search on the notes field in the employee. So here we go, and that's just there in your face, as easily as that. But this is easy. But what about this one? Somewhere, okay, it's here. I don't want to do a lot of work. So RavenDB pops it out for me. In this case, this is trivial. Here is another example. I can take, you can see that I have,
that goes right into the next question that there is. So this is full text search, what you did there?
Correct. This is full text search. But before we get to the next question, I want to show you another thing. Okay. Look at this thing. Let's say that, what do I have that is interesting? 1 second. I need to find, let's do this. So now, so I added this. I have an attachment to this document. Now I can do something. Just to give you some context, what I'm doing here is the name. Now, let's see if I remember how this is done. So this is.
So the content in that temp file is now indexed or searchable.
Yeah, okay. It's not quite like this because I'm doing that off the top of my head, but now you have the ability to do that directly. Now I can do something like this and say, hey, I want this to be full text search.
Amazing.
What was the problem? So this works, and this is the problem. What's the problem? So now I can go and look. So probably mess something up with regards to this, but this is more or less how it would look like. And so now it bugs me. Give me a second, I will fix that. Other way around.
So you essentially have a .NET method representation for that. So that is looks kind of like .NET in SQL.
It's literally that, yeah. And I don't need to think about it. I'm temp.txt, that's what I mean. And now I can attachment. And what you return is an attachment object with get content as string. No, get content as string. That's what I want. Oh dear God, Sorry, I'm being stupid. Now, index terms. Is Oren.
Yeah.
And now I can do this sort of queries, and just to you understand, so think about what I just did. I have an attachment. That attachment is now available during the indexing process. I can go and pull related data from other documents, stuff like that. Suddenly, the entire concept of what is database and what is available for you is changed significantly. We have a question from Andreas about Lucene and coax. It goes like this. For full text search, RavenDB use the Lucene structure, Lucene database engine. What we've been working on now is a database engine called coax. Now, the idea here is that we're able to provide better performance, better integration. The coding style that we have for Lucene and internal stuff are very different. Lucene was written in Java, ported to .NET. It's still far beyond the current Java version. But the key aspect from our perspective is that it is not following what we consider to be good coding practices. Now, good coding practices for database engine written in .NET are very different than standard idiomatic.NET issues. And that's something that you have to take into account. Coax is going to be in the next version of RavenDB, but only as an experimental feature. We have high hopes for that. It is already able to do things that I'm going to show you. I probably shouldn't, but whatever.
Is that also written completely in .NET now? Or?
Correct. Everything is written in .NET.
So that is one really amazing thing, that you can build a database system like RavenDB, which is super fast in .NET.
Yes, it's but again, a lot of that is not standard .NET. This is the code. By the way, RavenDB is open source. You can go and look at the code. github.com/RavenDB/RavenDB. And I want to show you, it actually ties very nicely to the current topic. I want to show you what some of the code looks like. And here I have, let's go. Okay. This is a fairly trivial piece of code. It implements a set. Now, just so you understand, this is a set of long. The features that we support is add, remove, seek to value, iterate, forward, and back. That's about it. Now, I'm going to ignore right now the issue of what the database, how the database actually stored data, whatever. What's important to understand is that eventually we get down to something called a page, which is 8 kilobytes in size. This is being implemented by this particular code. But I notice this is a struct. Why is it a struct? Because that saves us allocations. This is a class because it's holds relatively large amount of stuff. And now you end up with code that looks like this. And you can see that there are things here that you're not familiar with.
Yeah.
Pointers and unsafe code, and look at the length of this method.
We're actually doing a lot of these things as well in hot chocolate for the GraphQL server to speed things up. Also,
because
like
performance matters. Absolutely.
And because this is a platform, like this is not the typical business code. This is an application where other applications run on top. So, like also we use a lot of memory pinning and things like that. But yeah, it's impressive. But it's impressive that .NET allows us to do that.
Yeah, and that's we have Adam that says that LiveHub.NET feels like a first-class citizen, and I think that the fact of look at this function, and I'm looking at on the one hand number of arguments, the number of pointers, the amount of that's going on here, but I get the ability to look to very tightly control exactly what's going on. And this particular thing is at the heart of optimizing queries. This is why I can go to this here, an issue query, have it come. Why are you doing that? Oh, it was offline. We dropped it to the disk. Now it's okay. Now we can search 70 million items in 0 milliseconds. By the way, just to give you some context, I'm going to let it run. This is now, I have two versions of this index. This index is running, Corax, this is running Lucene. And by the way, when we asked about what RavenDB does, here is some of the things where it matters. So you can see that we took, this is the amount of CPU time that we took to index this thing using Corax, and we'll see how long that takes.
Oren, there's another person who has a question, Martin. You can unmute.
On that topic, I've heard from people trying to develop high-performance software in Java for financial sector and stuff. It's pretty tricky that you have to know a lot about internals of the language, standard library, and so on to figure out where allocations can even happen with all the boxing that's going on. I don't know if you can speak to that, but would you say that C# is a bit more ergonomic, or is it about the same?
No, you have to. I want to show you something. So, come on, this is the reference presentation, right? So let me show you. So the trivial example, I have a string reader. Oh, come on. I have a string reader, and this time I hope to get access to reader. Here we go. I have a string reader, and look at those values. They are a pain. You have to know that if you're using a string reader, then you're going to allocate a 4 kilobyte of buffers, which isn't actually 4 kilobytes, it's actually 6 kilobytes, because this guy is for chars. And so that's 2 bytes and something like that. So those are just the sort of things that you need. And you see this? This sucks. But you just know that you have to do with that. So now you start knowing, oh, I know that I'm working on something like this, that I need to do a string reader. So what I'm going to do, I'm going to keep that instance around and maybe replace, maybe I have in here. So in here, I'm going to give you a wrapper instance. So a string reader, wrapper instance, the actual string that I have. And I'm actually allocating another instance around that. Why is that? So I can replace the inner stream that I have here, called discard buffer data, and keep on using the same instance, which saves you 6 kilobytes of allocation each time. Here is another interesting factor. Where would that be? That would be in a fixed size set. So fixed size. Behold this guy. I actually have something that was more interesting. Check something. Here we go. Behold this one. Now, just to give you some idea, this is how you run a range query. Now, let me show you the usage. This is where, no, not this one. I don't want this one or this one. This is how you do a greater than. So exclusive on the bottom, inclusive on the top. And we're passing all of that. And now we're calling this, which ends up, so I know this one, calling this one. Why do we do it like that? Why not pass a Boolean? Well, you see this guy? This is a type. Now, I know that the way that it works is that when the JIT compiles that, it's going to say, oh, I'm now looking at the exclusive version of this particular code path. I'm going to eliminate that code entirely, which means that every time that this is called, I save the branch. And it may sound like, what's the deal with saving a branch? But branching is a killer for performance. And here is another one like this. And by the way, notice that I have an actual go-to here. And here you can see how I'm specializing the code. And again, not the sort of things that you want to write on business applications. But as a platform, the fact that I can try to imagine that I'm debugging some code. And you know what I'm going to do here? I'm going to write the ugliest, most allocation heavy, whatever command, console write line to figure out what's going on. And I can do that. I can use string interpolation. It sounds like a small thing, but it actually is something that has a huge impact on the overall health of the system. In line 199, we are doing something very strange. We're casting to object to cast too long. Why is that? And this is a question from Stefan. Because core val is a t-val. See, it's this guy. But what's the problem with that? We cannot cast it too long. Why? Because there is the compiler doesn't know that there is a casting for that. So what we actually do, we erase the type. This would actually do boxing, except that it doesn't do boxing. I will show you. It's really fun to show. I think it's here. So this is what this looks like. This is when we are look at the box and everything. Now, if I look at the assembly, there is no boxing. On the other hand, if I had this, then now it's become more complicated, and I have to do the unboxing and something like that. So the fact that I'm doing this is actually being optimized by the JIT. Because it's, hey, I know what type it is. And then I know that, so it basically does a constant folding. And I can utilize that on generics. And there are a lot of stuff like that that we're utilizing. we do a devirtualization of course. Where can I show that? Here's an interesting example. You see that we have a tokenizer? And this is really, really strange. Look at this. This is an interface. Why do we do this? Look at where we have T. And we have doing this. And now we have somewhere a helper. Look at this guy. So what's going on? Here is lowercase tokenization. In this case, and there is another one that's somewhat more interesting. Why does it matter? Because look at how this is being used. So now I have this specializing for that. And the code in here is going to inline those codes. So if I'm going to take this particular code and look at the assembly, this does not happen because the JIT already knows that this is true. So we're able to play a whole bunch of tricks around those sort of things. More questions? Okay, so let's talk about database engines. We actually dove right into the code base, but let's go up a bit and try to understand what we have. So this is me, blah, blah, blah. This is the more or less structure of this talk. And I'm going to start with the internal structure of how a database is organized. One of the things that I used to ask people was, build me a persistent formula. I want you to write to a binary file for codes, and then allow me to search it. Now, I remember doing that in Pascal when I was in high school. And it was fixed records, and you can either have them sorted or you can have a separate sort on the side, but something like that. Not that big a deal. And for the past 5 years or so, I was asking these questions for all of our new candidates. And a lot of them never got it. A lot of them were basically like zero idea how it works. And quite a few of them actually did that using something like SQLite, Access, or something like that. My reaction to that was, dear God. Because people think that the database is black magic. How does it work? I don't know, it works. So let's go and focus on what's going on. So the whole point of a database is to store and retrieve data. And it matters a lot what is the format of the data. Some of the responsibility of the database is to manage resources, to handle transactions, to execute queries properly, but in the end, you give it data, you get data back, that's it. So now, here is a form of the application. This is a CSV file. What are we missing for a good database in this case? Well, to start with, what happens if I want to do a search? Well, it's easy. Just search like this. It's sorted. Is it? How do I go to record number 3? Turns out you can't. You can cheat. You can go to the middle of this file, scan until you find a line break, and this is your new record. But it's actually kind of hard to do, not very efficient. What happens if I need to add another bob here? I have to shift all of the canines down. If this is a large database, I cannot do that. So it's actually kind of hard to figure out how to do this. CSV is great, but it doesn't actually help me if I want to actually build a database. Great interchange format said that it was actually using this method. Here is something that's really annoying as a database guy. Did you know that there are specific ASCII characters for record separator, column separator, stuff like that? They are never in use. This is really silly. Okay. Some interesting details that we have to consider. How am I going to look up at my data? This is actually something really interesting. The whole trick, everything about databases, any database in the world, comes to one trick. Lookup on assorted data structures are fast. We're done, that's it. But you already knew that. So what's going on? How are we actually going to store sorted data in a file? And the key aspect here is that we can't just modify the data. If we want to insert a line here, we have to shift everything down. And AVL tree is the classic example. Redback tree, if you're fancy, they're great. But what happens when we throw them into a disk? This leads to really interesting details. Look at those numbers. This is NVMe drive. This is a hard disk. Notice that this is in milliseconds. We're not even playing on the same ball field, same order of magnitude. Now, we can easily prove the AVL tree is the optimal data structure for sorted data, as long as the access to any given point is the same. What do I mean? Let's look at this one. Here's a tree. It's a nice tree. This guy will only work if the cost of access this guy or this guy is the same, which is actually false. The cost of accessing this guy is actually cheaper than accessing this one in memory. Why is that? For a very simple reason. Here we go. You see those guys? I have 32 gigabytes of memory, but I have 3 layers of caches in the middle. And L1 cache is quite small. So that means that if this is sitting in the L1 cache, and this is not, this is going to be far, far faster. What happens if it's sitting on disk? So that's a problem. Look at the numbers. All log n, all log 2 of n, means that with 1,000 items, I have to do 10 lookups, 5 milliseconds, or 80 milliseconds if I'm using a hard disk. With a million items, things become far, far worse. With 350 million items, well, things sucks. Remember, we're going here to shoot to above 1 billion. So that's costly. So the first thing that we do is stop looking at individual values. We are not looking at rows. We're going to look at pages. And if you think about it, it makes a lot of sense. A page as in physical page, which contains many values. A page is a unit of memory, typically 4 kilobytes to 4 megabytes. RavenDB use 8 kilobyte pages. we load them as a single unit from the disk, and we write them as a single unit to the disk. The whole idea is that we have appropriate locality of reference. But you don't have to guess about it. Let's look here. This is the live instance. Yeah. Was there a question? RavenDB contains many, many debug endpoints. So what I'm going to do now, I'm going to just do this. This is the database name. Now it's going to tell me, I don't know what you wanted. And now you're going to see something really, really interesting. What do we have here? This is the structure of the B tree for all of the documents in here. So here it is. And you can see here the documents. So each tree like this contains about 120 items. Now, let's say that I want to search for orders 777. How do we do that? I'm fetching the root page, page number 300. Where is order 777? I will increase the font size so it's easier. Can you see it? Well, it can't be here because order 77 is greater than this. I keep on going. It is here. How do I know? Because I did a binary search, and this is the fourth item that is smaller than the value that I'm searching for. And now, again, this is sorted data. Here is 777. Now, this is what's going on when I have 1,000 items. Let me see if I can do horrible things to this system. Okay. No, sorry, wrong. Here we go. Take a look at this one. I'm still rendering that. It might take a while and it crashes. What actually happened here, the server is having a fantastic time, but we actually killed Chrome. Let me try doing something here. Dear God, remember, this is us reading just the tree structure, reading this. And this might take a while. Again, we have 300 and something, 350 billion records. I'm actually not surprised that Chrome failed to do that. But you follow the idea, each one of those things, this is the 8 kilobyte size. It contains those items. Now, what is this size? This is 6, and this is another 6. So the average factor, the average size of an entry is 12 bytes. This is actually true because you also have another 8 bytes here for the value. And there is some metadata overhead. this is where you get into, okay, I need, this is the size of the page. I'm missing something because it's too small. I think I missed the, never mind. But I can pack 120 something entries inside of every 8 kilobyte size. It's still, wow, still going. Okay, that's kind of scary. And what's happening in this case is that it's cheap for me to do those lookups inside a page. I read one page in the middle of it. Now, here's how it goes. This is the structure of the bitry page. 6 are expensive, so I'm reading this one. And then I'm going to this one, exactly as we did before. All of these results come in one DSIC. This is the cost. Well, F is the fill factor. And as you saw, the fill factor in this case is something like 100 and something. Wow. Okay. Searching inside a page is effectively free. Why is that? Well, what's the cost of searching this page? It's log 2 of 120, which is 7. But 7 what? 7 operations inside of memory. Compared to reading it from the disk, this is nothing. There's another aspect that we have to consider. I read this. What's the size that I'm going to have to do? We'll see in a bit. The data structure is called B+3. It is typically used for disk optimizations, but it is relevant wherever you have memory hierarchy. Let me rephrase that. It's relevant everywhere. It's actually cheaper in some cases to implement a B tree than an AVL tree when you're operating only purely in memory. Why? Because this plays great with the memory hierarchy of all modern systems. And by the way, this is interesting. The first time that we have the B tree in academic literature is over 40 years ago. And even then, it was called the ubiquitous B tree. It was just the first time someone bothered to writing about it. And now I want you to see what's going on. Here is a fan out of 128. At the top, we have 8 kilobytes. Second level, 1 megabyte. Third level, 128, 60 gigabytes, and 2 terabytes. Why does it matter? Look at this guy. I'm still pushing that one down. I'm kind of amazed by this one, to be honest. But why does it matter? In this database, where is it? Here we go. In this database, I have 360 million items. If the fan out is 100, what does it mean? Let's look at it. So the bottommost level would have 3 million units. So we're talking about this one. The next level. So this is now the next level. Now we're done. So this is probably a 4-level data structure. And now let's look at this. Let's say that I have a very small cache of 128 megabytes. What is the chance that the root would be in the cache? And the answer to that is pretty much 100%. What is the chance that this would be in the cache? Also 100%. Chance that this would be in the cache? Kind of high. So we only need to query, to go to this for these two. It gets more interesting. What happens if I have a local operation that I'm currently doing here a lot of work? This would be in the cache. This is going to be an amazing performance for us. just because of the structure of the data. Remember, this is sorted data structure, so all of the usual things apply. But instead of doing a lot of jumps, we can treat it as locality as a core concept. Now, at some point, I am not unable to to write more details here. So I'm going to insert HANA into here, and I run out of this space, run out of space in the page. So this is when I do a split. So this is the root page, just one page in this case. Now I split it. You see how it works? In this case, I insert HANA as the last item. So I was able to just create a new item. This means that this is a very dense page. Conversely, what happens if I would insert then? Here I have two empty, and here I have two empty. Now I have internal fragmentation. Here is the same set of data. In this case, I insert that in a sorted fashion. In this case, I sorted that in an unsorted fashion. So I have a lot of empty spaces like that. This has an impact on the height of the tree. And the height of the tree has direct relationship to the cost of the query. If you're familiar with database that tell you, oh, the cluster key always should be some form of a sorted data structure. Why is it bad to have a GUID as the primary key, for example? Because you generate this sort of bit trees. Why is identity so good? Because you generate this sort of bit tree. Then that's about it. Okay. Here is a question. How do you treat bit tree? There are two ways of handling it. In one way, in here, we are storing the value itself. Here is order 777. You can see that the actual size of so it's very fun. Order 777 size is 888. I did not do that on purpose. So you can see that I could put in here the sizes. But I have 8 kilobytes in here. If I would be able to put just 8 kilobytes in here, if I have to put almost a kilobyte for each one of them, then each one of the leaf nodes would fit about 4 to 8 items, which would mean that the tree at the bottom would have far fewer items in here. And then I would have far more branches. Conversely, this is when the data is embedded in the data itself, in here. Conversely, I may just have a reference to somewhere else where the data is. What's the difference? This is, by the way, what we're doing here. The 8 here is the ID of the data on disk in another location. What's the difference? Well, consider what happens if I need to do a search. Well, I need to search everyone whose name from B to C. So in here, I'm going to here, and here. 3 operations so far, 3 pages that I have to see. Read whatever from here. 4, 5 pages that I had to read. Okay, 5 pages. In here, I go to here and to here. 3 pages. It turns out this matters for quite a lot of reasons. Because if you need to do a lot of scans on here, that actually reduce the amount of data that you scan. There is a downside that now that I have this value, I have to go and do a lookup. Whereas here I already have the value. Here I have to do the lookup. Another issue, what happens if I have a large value that cannot fit into a page? Well, it's easy. I'm allocating however many pages I need to put it and just store a reference to that. This is called overflow. this is the, by the way, I'm running through things because some of that is very low level stuff that you might not care about. If you have any questions, please stop and I will give it more details. So this is the internal structure of B3 page. You can see that we have some metadata about the page. This typically takes 64 bytes inside of RavenDB. And we have these two items, the lower and upper offsets. Whenever we enter an item to the page, you can see it here. I'm going to enter entry number 1, which is B. So I'm writing it at the top of the page, and I'm inserting that, the reference to that to the top of the page, etc., etc. Why do I do that? This is just a buffer. I don't care about this. This guy, which is an array of shorts that points to the position of each one of those, is sorted. So the idea here is whenever I update an entry, I insert something, I can just move those values out of the way. And those tend to be, they are shorts, or they are very small. We can actually see that if we go to 3CS. Add. I'm just going to show you what we're doing. So what happened is that we say, give me the relevant page. And where is somewhere around here? Here it is. So now if I have a space for that, ignoring all sorts of stuff that we don't care, data node. So now I need to create the node. And somewhere around here, I'm copying the key and allocating the node. Index is the position in which I'm writing the actual value. And now you can see that I'm actually making room inside of the offsets. And okay, so the whole idea is that I can put things in here in an easy fashion. It doesn't cost me a lot of operations to move a range of shorts. Imagine that in the case that we have here, the total size here is 252 bytes versus here where we might have close to 8 kilobytes that we are storing. Okay, so now that we have a sorted data structure, what can we do with that? Well, we already saw how we can search for 777, which is here. We can also do a range scan. What is range scan? Give me all of the orders in the system. How do I do all of the orders in the system? I scan through here, find the first order, then continue scanning all of those until I run out of orders. So range scan or prefix scans are trivial. And now I do a get by ID. I do a search. If it's a cluster index, I just return the results. If not, I have to load the related data. That's about it. Now, let's talk about how do I do that with an index. Not here. Scan index. This is the index. If I assume at least most of you are familiar with what we actually have here. So the idea here is that we have another data structure, another B-tree that is sorted by, in this case, by the registered or something like that. And we can search, give me registered in the name, and then we can scan through the index and load the related values. And this is the comparison function that we have, first by register descending, then by name ascending. Everyone follows how it's working? I'm throwing a lot of stuff very quickly. If there are no questions, I'm going to assume that I'm clear. So let's talk for a second about what is a raw ID. Here, I'm just saying whatever raw ID is. There are two types of raw IDs. In the first, the logical manner, this is the primary key of the record. I have to do another lookup to find it. Let's say that I'm doing this sort of search, and the row, this is the user ID. So I have to go and find, I have the bit tree of the user IDs, and I have to search that there as well. Physical means that you can go directly into that. Notice that he says impact on the cost of this query. Because if this is a logical system, for every result that I'm getting, I have to do a log and search. In this case, this is just a one operation. It doesn't impact the complexity of the query. There is a great blog post from Uber Engineering, and this talks about, this is MySQL, and this is Postgres, if I remember correctly, and you can see the difference in how they work. In this case, the second index points directly to the record on disk. In this case, the second index points to the primary index. So if I'm saying, give me C to D, I said, okay, going there, going now. Going there, going now. Going there, going directly here, going there, going here, directly here. Notice that this step is actually doing a lookup. So doing a log operation on the primary index. So those are the queries that we can optimize. Key, prefix, and range. That's it. Everything else is compute. That includes everything else. Now, it turns out there are lots of tricks that you can do. You can do parallel scans of multiple bit trees and merge them. But in general, that's the core concept of how things are working. And that also matters with how do I do those sort of queries. For example, try to imagine that I have something like this. How would the database optimize something like that? Well, the answer is that this returns a different one whenever called. It cannot. But let's say that we have it here, like as a parameter. This works. We reverse that. So the idea here is that we now go 18 years back and now give me everything that is smaller than this value. Why is that? Because now I can do a seek to a particular location in the bit tree, in the dates, and then just scan upward, which is really, really cheap. Versus here, I have to fetch the birthday, compute against this, and then query. Just different ways of looking at the same thing. In general, we want to avoid as much as possible doing computation during query, because the more results we have, the more work we have to do. Questions so far? I've been rushing through things to make sure that we are in a good place. And I mostly talked about how the database internally organizes itself and the basic building blocks of queries. If you have any questions, this is the time, because I'm going to dive directly into really annoying aspects of databases. And that aspect is, how do you actually keep your data safe? What is safe? Safe means that if you put data inside of the database, you want to keep it back, even if someone pulls the plug. What do you do then? Well, this sucks, but this sucks like a lot. And why do they suck? Because they are slow. Even NVMe drives, even SSD drives, everything sucks. By the way, if you're in the cloud, this sucks and network sucks. So this is networks and this compound sucks. Basically, general suckiness all around. Why does it matter? It matters because those are the numbers that we have to deal with. Look at those numbers. Those are benchmark optimal scenarios. This is the part where you cry. Look at this. 1 nanosecond, 8 million nanoseconds. And by the way, there is also memory, which is a few hundred milliseconds, a few hundred nanoseconds. So even that you have to consider. Now, what's the problem? I'm writing to disk. How long is it going to take me to write to disk, you know? Pretty much forever. And here is where it gets interesting. Look here. What do I do here? I'm opening the file. I'm writing some data to it, and I'm closing it. I'm even doing proper things and checks for errors. Yay, I'm good. How many things can go wrong in here? Well, everything. But for now, let's assume that we created a file. We called write. And you know what happened? The disk was never invoked. The execution is now in here on the close. The disk was never invoked. Where did my write go to? Yeah, go ahead. There was someone who asked a question? No, never mind. So I made a write. That write never hit the disk. It went into a buffer somewhere. In fact, just to give you some context, in this case, I'm using raw syscalls. You'll never want to do that. You always want to have buffer syscalls. So you have user mode buffer, you have file system buffers. So you have kernel buffer, then you have file system buffer, then you have driver buffer, then you have a buffer on the disk, and finally you actually hit the platter. The time that it takes from you to write something to a file to it actually being persistent on disk can be measured in minutes. Why? Because otherwise this particular line of code may take you lots of time. Let me explain what is lots of time in this context. Here I have a database that is doing work. We are nearing the 400 million at this point. What I'm going to do, I'm going to look up the I/O statistics on this database. And what you can see here, here is a particular write to the database. I'm writing 2.37 megabyte, and it took me 1.92 milliseconds. Now, just to be clear, this is a really powerful system. But notice, this is almost 3 milliseconds. This is a powerful system. This is running on NVMe drives. And the amount of time that it takes me to hit the disk is measured in multiple milliseconds. So how long is it going to take me to write this? Forever and a half. So we're not doing that. We're writing to buffer and multiple buffer. So that means that if I successfully wrote this, but then I crash, what would happen to my data? Well, it wouldn't be there. Or it may be there, I don't know. There's no guarantee. But I closed. So now we're good? Hell no. A, I didn't check that the close succeeded. But B, I didn't what the operating system is going to say, hey, you just closed this file. There is a good chance that you would open that in just a few more seconds. I'm not going to involve myself with this. So I'm going to keep it in memory just in case. I will flash it at some point because writing this is so slow. So look at all of the buffers that I have here. User, OS, file system, driver buffer, this buffer. Sometimes there is network buffer in the middle, especially in the cloud. Just shoot me now. So I'm fixing that. I'm forcing us to do this. We're good, yay, right? We're not good. We are broken. We are broken to such a degree that it is horrifying, absolutely horrifying. Here's what happened. Fsync can fail. What happens if this fails? Here's the funny part. Oh, one knows. Literally, that's the definition. No one knows. You can make zero assumption. Data may be there, it may not be there. If you try to write the data back again, you open the file again, you write it again. No idea what's going on. Nothing is safe here. So there's a lot of, Dan Liu has written a lot about safety of files, but just to give you some example, this is the pattern that you have to do. A, do error checking, but here's what you have to do. Open the file, write in the file, fsync the file, close the file, open the directory, fsync the directory. Why? Because in here, you might have modified the size of the file. So you might have successfully persisted the data to disk, but you lost the metadata about the change to the size of the file. And now you have to do an fsync here, and then you close and now you're good. Except that you're still not good. And you know why? This is funny. You are not good because you also have to write the code to handle reading, which can be in any one of in these intermediate states, including, by the way, someone went and sneezed on your file, which is fun. By the way, if you notice that I'm excited about this, you're correct. I'm quite enthusiastic / upset / horrified about this situation. So, by the way, there is zero way to recover from fsync failures. Do you know what you have to do? You have to recover and redo all of the work that you have done. How do you do that? And the short answer is that an application cannot do it. A database can, and let's see how it works. So the problem here is that at any point I may have to fail, I may fail. And if I'm failing, I have to recover. So I cannot modify the data in place. What happens if I have a failure? So I have to do one of two things. I have to modify the data somewhere else and then write durably and then actually do that. There are two ways of doing that, two common ways of doing that. One of them is something called the write ahead log. I'm saying I'm going to do X and I'm writing that durably to the disk, and then I'm going to do X. And the idea here is that if you crash, you can recover. You read from the log, which you wrote to durably, and then you just replay everything that happened there. There are all types of logs. There is a redo log, there is an undo log, not going to go into exactly how it works. There is also another option, which is called the append only option, in which case you're never modifying data in place. You always add to the end of the file. The downside of that is that if I'm updating a single value all the time, then it keeps getting added to the end of the file. All of this data is crap. So I have to do a compaction, which means that I just wrote, let me just give you the context. This is now almost 360 gigabytes. If I was using append only, I would use a lot more of the disk space, and I would be running on the system with, now I have to write some part of the data and then delete the old file. So I do a lot more write, I do use a lot more disk space. Okay, so the write ahead log has some interesting aspects. I'm only writing to the end of the log because that is sequential. That's very nice. I'm only writing in durable mode. Durable mode, and you can see it here very nicely, is super, super slow. Remember, this is an NVMe drive. What I can already see, where is it? NVMe drive. Here is an NVMe drive when I'm writing basically nothing. Less than half a megabyte, and it takes me 24 milliseconds. Notice the speed at which I'm doing that. Why is it so slow? Because when I'm writing, and you can see this is journal write. When I'm writing to the journal, I require that this would be a durable write. So it has to skip all of the buffers in the middle. And this is a NVMe drive that is supposed to be able to do 100,000 operations per second. But those 100,000 operations per second assume that there is a buffer in the middle, which is set for databases. So I'm writing the changes to the file before making that. And it's very much set a page X to a value Y, and I'm writing that. And only if in a replay, I can do all of those operations to the system, as this is. Something that we have to consider, and this is the network protocol of the database. And we have two models, the chat and the message. What is the chat model? This is SQL. Open transaction, insert into, select from, update, commit. Why does it matter? It matters because each separate statement is a different network round trip, which means that for a database with this kind of model, you have to keep transaction open while a user is waiting on the other side, or network is waiting on the other side, which means that the latency of your transaction is measured in seconds or minutes or hours. There's all those horror stories of the guy who opened a transaction at 9 a.m. and committed at 5 p.m. And as a database guy, the only reaction to that is puke. Puke, 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 all of that. The other option is that you get a transaction with all of the operations that you have in one shot, so you can execute that immediately. And that has major impact on how you do the write-ahead log. Because can you just write a transaction in place with the write-ahead log? Do you have to write the changes and keep them around the previous version, the current version, as the user thinks about the transaction? So here's how it works. One option is to use write and fsync, but this means two system calls and can be really expensive. One of the issues with fsync is that the kernel is going to flush everything that goes to that particular drive, not just your writes. You can use OpenDsync and write, which is slightly better. But again, this is roughly the same thing as that. For durable writes, we typically use something like this, ODirect and ODsync. What this means is basically an instruction to the operating system. Don't do any buffering. This implies that all of the write must be 4 kilobyte aligned, so it can do direct memory access to the hardware. It says here, those things together send a flag to the hardware, which is called FUA, Forced Unit Access. And those means that it goes all the way to the disk. The disk knows that it has to commit that when it acknowledges this write, it is persistent. Now, after the commit happens when this is done, which is great. But notice that there are a lot of concerns. First of all, the fact that once we are done from the write, we're okay, is great. But what happened in the middle? We may have partial rights. For fun, there is absolutely no guarantee on the order in which the disk would commit the changes. It is possible that I have 0, 0, 0, and then the data, because it decided to write it from the beginning to the end, or from the beginning, or something like that. You have to worry about the file size, because if every time that you write and you do an append only, you're generating the same, you're extending the file, then you have to do the usual dance of, okay, let's open the parent directory with fsync that. So you want to extend the file in advance and then operate on that. The ideal scenario is that you're only writing to the log and you're never reading from them. And that's the best case scenario. There is how do you replay the log? You basically, that depends on your structure. Do I have to read from the database? Can I just issue writes and stuff like that? Remember this, writing to the log is really, really slow. So what we can do, we can play around with that. So instead of, I have 3 independent transactions. Instead of writing each one of them, for each one of those, I would pay the cost of 1 to 34 milliseconds. I would aggregate all of them together and write them in a single shot. The primary cost for writing to the disk is the system call, the actual writing disk. The size that I'm writing doesn't matter that much. So I can do transaction merging. And another thing that is interesting, look here, this is serial execution of merged transactions. I can start the commit process, and this can take multiple milliseconds. If I'm using hard drives, it can make multiple seconds. It's actually quite common to see seconds in it. In that time frame, I'm already starting to execute the next transaction. And why am I doing that? Because if this fails, I can just abort this transaction entirely and continue from there. So this gives me an additional parallelism between executed transaction and writing to the hardware. There's all sorts of other tricks that you can play with. Let's see here. Here's a good one, I think. See here. Now I'm writing 3 megabytes to the disk. But notice what I have here. I started with 4 megabytes. And I compressed that. Now, in this case, it's not that interesting. Because the data, but we did manage to save almost 50% of the data. In certain cases, the cost, see here, it probably wouldn't be that much because we're running on NVMe. But we are currently running with just those writes going on. A single database, not much work happening in the background. What happens if we have a lot more work? Then reducing the amount of data that we write can be a significant boon to the system. So that's another optimization that we can have. Questions so far? Okay, maybe you need to commit to those questions. Okay, transactions and concurrency. Problem. The primary issue that we have, one primary reason we want to have transactions is to control concurrency. So 2 users who are modifying things at the same time are going to see consistent behavior from the database. Here you have to consider what is the protocol. If we have the chat protocol, then we have to keep things in place with parallel work going on and things like that. Almost always go to single-threaded writes. Why is that? Because it drastically simplifies systems. But what does it mean that we have single threaded writes? I want to have concurrent operations. Well, remember that we talked about doing transaction merging. The idea here is that I'm going to accept transactions from the network as complete units. Then I can execute them one after the other. It simplifies my life considerably in terms of the complexity of concurrency inside databases in general. But it also ends up actually being faster in many cases. Why is that? If I have concurrent transactions that modify the data, what if I have two users who try to modify the same record? Well, one of them is successful, one of them is not. I have to do a log for that. There is a really nice paper called OLTP to the looking glass. And the lock-in and latching is 30 to 40% of the cost of overall operations, which is absolutely insane. If we can do that as single-threaded, all of the loss goes away, and it actually simplifies a lot of other operations as well. So let me show you an interesting scenario. There is something called MVCC, multi-version concurrency control. And here's what's going on. I'm reading page 4 in transaction 12, reading page 8, and now I'm in transaction 13, reading page 8. Both of them are saying the same thing. Now I want to modify page 4. I can't modify that in place. Transaction 12 is currently reading from that. So I do something called CAR, copy on write, and I copy it to the side. And I modify it for transaction 13. Whenever I ask for page 4, I'm going to go here and get Emily. At the same time, transaction 12 is going to see Kate. The whole idea is that I don't need to have locks. Why is that? Because we are not referring to the same item. Which, by the way, means how do I roll back a transaction? Well, let's free all of those things and I'm done. I haven't actually modified it. How do I commit a transaction? I publish those set of changes. The next transaction is going to know that page 4 points here. That's how it works. And it is also going to, if we have another modification, it's going to have another copy of page 4. So we may have multiple versions of the same page in memory at the same time. We have a question from Stefan about locking and latching. Locking is at the page level. We have a page lock. Latching is at the record level. No, sorry. No, I'm wrong. Let me see if I can remember. There is a specific, here we go. Okay. So latch is, so lock is on a database page, and a latch is on the in-memory data structures that not on the page itself. So I will reflect. Let me. Lock can be on a row, page, or a table. Latch is on in-memory data structures. So, for example, maybe that you want to allocate some more memory, you have to go to this, then you would have a latch on the in-memory structure while you're using that. Very short-term operation. Whereas lock is for the duration of transaction, which can be seconds to hours. Okay. So the whole idea here is that I have multiple versions. And the commit is basically publishing the page translation table, the map between the current one and the next one. And again, see here, I have page 8 remains here. Page 4 is here. If I modified it again, I would have another one. Transaction 13, transaction 14, etc. Notice that I have multiple concurrent versions at the same time. I'm going to resolve that when no one is looking. So when I know that, look here, if there are no, if there are, the latest transaction that I have is transaction 15, what does it tell me? It tells me that no one is looking at page 6. Why is that? Because all of the transactions are going to take from here and know that page 6 is here, page 2 is here. So we are free to modify them because no one is looking. I cannot modify page 4 because there's still a transaction looking at it. I cannot update it to able because it is modified here. So the whole idea is that we are waiting until no one is looking at the data file based on the page translation table of the latest transaction that we have in place, and then we operate on that. Atomicity, a transaction has a snapshot, complete snapshot of the system. How is that? Because I have the notion of the page translation table. And the page translation table contains all of the pages that are modified by all of the previous transactions that aren't currently in the data file. What I'm guaranteed is that as long as I have a transaction open, they cannot change because I cannot write to the data file until all of transactions have progressed beyond that one. The page translation table happens automatically. Isolation, if they're isolated, we have a single writer, so everything is happen quite easily. There are no locks whatsoever because we can just do this sort of thing publish atomically. And durability is maintained through the writer header. Writing to the data file is complex. Let me show. Okay. What you can see here is several things. In this case, here's the compression. Here is the write to the journal. And now here, I have something called a flash. What is a flash? Is when I'm moving the data from here to the data file. But remember that the disk is slow. I'm not doing that in a durable format. Instead, I'm just writing directly to the file in a buffer manner. And then I'm going to call fsync on the file. You can see, since the last time I called fsync, I modify 1 GB. And it took some time to run, almost 1.5 seconds. And you can see some other scenarios like that. Now, why are we doing it like that? Because you can physically see how this works. Lots of small transactions, and eventually we have a flash, and then we sync it to the disk. The whole idea is that all of those can and we can actually see happen concurrently without stopping one another. And after we did the sync, now we know, now we have guaranteed what is actually happening in the data file. Now we can trim the log to free the disk space that is responsible for that. Now we can free all of the SCAD buffer that is required, that held the temporary data outside of the data file itself. I'm not going into there, that's too low level, and I think I went way overboard. Some tricks of optimizations. We have to consider what's faster. the disk on the CPU. We actually can see that very nicely in here. Here is 4 megabytes that we're writing in 3 milliseconds. And here I spent 3 milliseconds to compress that by just a bit. In this particular case, I'm cheating somewhat. I actually enable a higher level of compression above, so we're not seeing as good a compression rate as you would normally see. Otherwise, we would extend that by a lot. By the way, I don't know if you noticed, but RavenDB used to take a lot more disk space previously. And what basically happened, we wrote to a lot of journal files, and then we could throw them away. So even though we have almost 500 million items here, we're not taking that much disk space. So this is one trade-off. So writing the log file is expensive, especially because we're almost never reading that. We can also, what are we writing to the data file, by the way? We're writing the full pages because that's simple. But we have the previous and the core version of the page file. We can do a diff and write just the changes. So we have several steps where we are removing redundant data that we don't need to worry about. We can also do prefetching. So I know that I'm going to, I'm starting querying here. I know we need all of those. So I can tell the open system, go ahead and fetch me all of those right now. Buffer management is really complex. I actually have a whole set of blog posts about that. I'm not going to go into much detail. But if you're interested, I would recommend that you go and look into that. Because you have to manage, optimize reading from the disk, how much memory you're using, when do you discard that. Postgres is something called the TQ model, which is really interesting. There's a whole bunch of them that is interesting. You can also cheat and just use mmap, in which case the person who is responsible for doing that is the kernel, responsible for what is in memory, what gets thrown to disk. And the kernel also has global view, and presumably it had been optimized more than what you can spell. You can also give all sorts of meta advice, hints to the operating system to decide how to work with that. If you're working with multiple nodes, then you have to consider how do you show the data. You may have writes in multiple locations. It actually ends up being much easier in non-relational databases because the model works better in that case. You can have the write master and read replicas. This is how MongoDB does it, for example. That has issues. For example, GitHub had 40 seconds of downtime. They tried to switch the write master from one node to the other. Not all the nodes got it in time. And as a result, they messed up the consistency in the cluster. They had 24 hours of outage because of that. etcd, for example, Zookeeper has this notion of leaders and followers. RavenDB has the notion of multiple writers, so you can have writes going on in multiple servers at the same time at the same point. There's a whole bunch of ways of sharding the data and how you get to big scale. I'm not going to touch that too much. Just some interesting numbers about failures. Failures happen all the time. All the time. I just had a support call with a customer. They complained about seeing high network charges from Azure. And what ended up happening was that in the space of 4 weeks, they managed to lose 3 out of 3 nodes in the cluster. That's bad. But what actually happened was that they're running on a memory with local NVMe drives. And Azure, the host, had some issue, and they basically wiped the instance and brought it back again in a new host. So the data, this was effectively lost. the nodes will merge the data from the other nodes, so the replica handle that. And the customer wasn't even aware that it happened. But when we actually look at the metrics that we had, we says, oh, you actually replicate the entire data set 4 times or 3 times within that time frame because you kept losing nodes. And this is, without a doubt, a really scary thing because those are things that just happen. Sometimes they send an email, sometimes they don't even bother. But you have to really be aware of that. For fun, the moment you have one error, the chance for the next one is wow. Like it happens all the time, and you have to assume that the network is hostile all the time. But here is an interesting factor. You have dictionary. Let me show you. This is. Did you know that Microsoft made dictionary store on purpose? But the fact that you can go and look up the code of the runtime and the base library is absolutely freaking amazing. Here we go. So we don't care about this. Let's go to string dot. Come on. Here we go. Yes, it does. Come on, you suck. I can't find it right now, but the basic story is that you cannot trust this. So what actually, so what happened is that, what happened if I give you values that would collide? So different string values where the hash code would collide. Then that would turn a dictionary into effectively a linked list. And this is a denial of service attack on your system. So you know what we do at this point? Well, we intentionally create, there is something called cpash. That make it, make the hash function more complex and randomize. There is randomize. I know that, I saw that. So that really bugs me that I remember something that I can't. Here we go. That's the one. Okay. Defense in depth. Now you can see that this is using. And again, this is intentionally making things more broken. And you never want to use this one. I don't recall where we're using that somewhere. There's somewhere where this is actually being instantiated and used. And then it's in here. Oh, it's internal class, I think. So then you call this and ordinal this, but that's the basic idea. And it intentionally is doing something like that, which is really funny if you think about it. But you have to consider all of those sort of things. Okay, sometimes they are hostile by accident. But this is a nice, really nice story about causes for bugs. You can see that misconfiguration is 35% of the bugs, more than anything else. Why is that? Because you mess something up sometimes in a way that is evil. Someone told you that try to imagine that you push the configuration, but the timeout for a network call is 0 milliseconds. In this case, you can only send an email to people nearby. And there is a really famous case, let's see if, here we go. This is a great write-up about this. You cannot send email more than 500 miles from the office. And some of those things are behaving in a really, really nasty manner. In general, simple architecture is the best thing you could do. If you want to be scalable, put a queue. Always put a queue. It's amazing. If you can separate operational queries, that's easy. Read replicas are very easy, and they can make it tolerate errors a lot easier. And something we need to see, if you spend the time to do that, you can typically get order of magnitudes better with not too much complexity. And that's it. I think I'm way offline, but thank you so much for staying here and listening to me. Do you have any questions? Or did I just, yeah, Martin? I think you can.
I just saw the blog post that you shared where you wrote something. How do you like SIG compared to other programming languages?
I love it. Compared to C or C++ or Rust, I think it's the best unmanaged language that I ever worked on. It's really nice to work with because you can you work at the right level. Everything is there. At the same time, Z gives you the deferred flexible what is here. The downside compared to C# is the maturity of the tooling and the environment, but it's my favorite language after C#. And it's for unmanaged tasks, it's just very easy. Especially because when you're writing something like Rust, then the complexity explodes. The downside is that this is an unmanaged language. And some of those are really, there are certain scenarios that are really complex to deal with. Here's a good example. Look at this scenario. I have, let's say that I'm writing unmanaged language. I'm doing a set ABC, get ABC. Now I'm doing a set ABC. Now I want to use the buffer from here. How do I do something like that? Turns out, really complex. And this is basically a concurrent dictionary, which is just, I reach out and it's there in C#. And if I'm using another language, then it is, if I'm using Zig or C or something like that, it's far more complex. Okay. One last chance to ask any questions that you have. If there are any, then I thank you very much. I had a really great time talking, and I'm sorry that I took so long, but I hope I was I'm able to convey all of the information. Thank you, everyone. Goodbye.
All right. Thanks a lot, Oren.
Goodbye.